Section: Introduction. In this section, we outline our approach to machine learning, which typically follows a workflow of data collection, pre-processing, model selection, training, evaluation, and deployment. While this ideal scenario suggests a smooth process leading to user satisfaction and a chance for a break, we know that reality often disrupts this flow. The real world is dynamic, and data needs change over time. New datasets emerge, and old ones may become outdated due to issues like fairness or bias. As knowledge evolves, so do our concepts. For example, the design of phones and cars has changed significantly over the years. This constant change means that to stay relevant, we would ideally need to continuously retrain or fine-tune our models, which is not practical. Those of us who have deployed models understand that we face ongoing challenges stemming from the static nature of deep learning models, which are tied to vast numbers of parameters. We believe that a better approach to representing visual knowledge in deep learning is to create models that clearly distinguish between representation, how we depict information, and visual memory, what we actually know. We propose that deep learning models should incorporate a flexible visual memory that allows for explicit knowledge utilization and modification. In our work, we develop a straightforward visual memory for classification, showcasing 7 key features. These include the ability to easily add data at various scales, remove data through machine unlearning and memory pruning, and a clear decision-making process that we can adjust to influence model behavior. Our primary aim is to illustrate the advantages of a flexible visual memory from multiple perspectives. Technically, we focus on simplicity by retrieving the nearest neighbors in an embedding space along with their labels to classify images. This method helps us explore the benefits and limitations of a basic visual memory mechanism and identify areas for potential enhancement with more complex systems. We hope that by highlighting the clear advantages of a simple visual memory, our article will contribute to discussions on how knowledge should be represented in deep vision models. Some key points from our article include improved aggregation of memory samples through a new method called rank voting, which outperforms previous techniques. We achieve high accuracy on ImageNet validation and demonstrate that our visual memory allows for perfect unlearning, scales to large datasets without extra training, and enables control over sample influence through memory pruning. The idea of visual memory has been explored in various fields, including machine learning, neuroscience, and psychology. For instance, in psychology, exemplar theory suggests that humans recognize objects by comparing them to examples stored in memory. In machine learning, before deep learning became prevalent, instance-based learning was a common method. Recently, hybrid approaches have emerged, combining the strengths of model-based and instance-based learning. To build our retrieval-based visual memory for classification, we start with a dataset of images and their labels. Our classification process involves 2 main steps: creating a visual memory and performing fast nearest neighbor inference using that memory. Section Summary. In this section, we discuss the challenges of maintaining deep learning models in a constantly changing real-world environment, emphasizing the need for a flexible visual memory that allows for easy updates and control over knowledge representation. We propose a simple visual memory mechanism for classification that enhances model performance and adaptability, while also introducing techniques like rank voting for improved sample aggregation and perfect unlearning capabilities. Section: Building a visual memory. In this section, we describe how we build a visual memory. Our visual memory retrieves pairs of images and labels from a dataset when we make a query by finding images similar to a test image using a model. This model is a pre-trained image encoder, meaning we do not train it further when adding new information. We do not store copies of the dataset in the visual memory. Instead, we extract feature maps from the model based on a set of images relevant to our classification task, like a standard training set. For our experiments, we use features extracted from datasets such as the ImageNet-1K training set with encoders like Dino v2 and CLIP. When we have a pre-trained image encoder and a dataset of image label pairs, we obtain features for each image in the training set. We then create a database of these features and their corresponding labels for classification. For both Dino v2 and CLIP, we utilize the last image embedding layer as our feature space. For retrieval-based classification, when we have a query image, we extract its feature map and then query our visual memory to find the closest feature vectors. We use cosine distance to measure similarity, which is standard for models like Dino v2. The closest neighbors are ordered by distance, and we assign a weight to each neighbor, aggregating scores for neighbors with the same label. We then assign the label with the highest score to the query image. We implemented visual memory retrieval classification using two approaches. 1. Fast inference with matrix multiplication on GPUs, TPUs, where we save our visual memory as a matrix and compute the dot product with the encoded query image to find the nearest neighbors. 2. Fast and scalable nearest neighbor search using SCANN, which allows for quick lookups in large databases. We analyze the reliability of retrieved memory samples from the first to the 100th neighbor. As expected, reliability decreases with more neighbors, but even distant neighbors provide useful information about the true class. This leads us to investigate the best way to aggregate this information. We tested several weighting strategies for aggregation: plurality voting, where each neighbor has equal weight; distance voting, where weights depend on the cosine distance to the query image; softmax voting, which uses the softmax function for weights; our proposed rank voting, where weights are based on the neighbor's rank in the ordered list. We found that existing methods like plurality and distance voting often perform worse as the number of neighbors increases, suggesting they overvalue distant neighbors. In contrast, our rank-based voting improves performance with more neighbors until it plateaus, which is ideal. Our method also outperforms the baselines overall. We further explored how to enhance aggregation using the Gemini 1.5 Flash model. By adding the 50 nearest neighbors from Dino v2 for a query image into Gemini's context, we achieved a significant accuracy improvement. This shows the potential of using vision language models as a visual memory re-ranker. Throughout our analysis, we primarily focused on non-Gemini ranking methods to keep our exploration simple. Section Summary. In this section, we describe our visual memory system that retrieves image, label, pairs from a dataset using a fixed pre-trained image encoder, allowing for efficient classification based on feature similarity without storing dataset copies. We explore various aggregation strategies for neighbor retrieval, finding that our proposed rank-based voting method outperforms traditional methods, and we demonstrate the effectiveness of integrating neighbor information using the Gemini model, achieving significant accuracy improvements. Section: Capabilities of a visual memory. In this section, we aim to highlight the concept of machine visual memory from various angles. We focus on flexible lifelong learning, which allows us to add new out-of-distribution classes, including both data and labels. Standard classifiers, whether they are trained end-to-end or use a linear classifier, struggle to incorporate new information without retraining. For example, introducing new classes or modifying labels typically requires us to retrain or fine-tune the model. In contrast, a retrieval-based visual memory can naturally and flexibly handle such updates, aligning with lifelong learning needs. To test this, we added data for 64 new classes, along with their labels, to the visual memory of a pre-trained Dino v2 VIT L14 model, in addition to the existing ImageNet training set. We sourced these new classes from the NinCo dataset, which is specifically designed to have no overlap with ImageNet. This setup challenges the model to apply its existing knowledge to new, unseen concepts. The task becomes more complex as the model must retrieve images from both in-distribution and out-of-distribution classes. Ultimately, our visual memory now includes 1,064 classes, 1,000 from ImageNet and 64 from NinCo. Our findings show that with visual memory, we can add new classes while maintaining in-distribution accuracy, with only a slight change in performance, and achieve high accuracy on the new out-of-distribution classes without any retraining. Next, we explore how visual memory scales with increasing model size. We hypothesize that larger models can achieve similar performance to smaller models with less visual memory. This is because larger models should be better at extracting features, requiring fewer examples to represent different concepts. We empirically examine this by analyzing various sizes of Dino V2 VIT models and CLIP VIT models. Our results indicate that as we increase the size of visual memory, the error rate consistently decreases for each model. Notably, even with just one example per class in memory, the performance on ImageNet validation is significantly better than random chance. This suggests a flexible trade-off between model size and memory size, where smaller models with larger memory can match the performance of larger models with smaller memory. We also tested the ability to add billion-scale data without retraining. We combined the ImageNet-1K training set with a subset of the JFT3B dataset, treating JFT as unlabeled and generating pseudo-labels using a powerful classifier. Our analysis shows that even with this large-scale data, increasing memory size continues to reduce validation error without any training. The most significant improvements occur when we have fewer samples in memory. To assess whether the benefits of increased memory size extend to out-of-distribution data, we compared the performance of the Dino V2 VIT L14 model with ImageNet training data in memory versus JFT pseudo-labels. We evaluated the models on several datasets, and our results indicate that visual memory scaled with JFT data enhances out-of-distribution performance across all datasets compared to using ImageNet-based memory. Overall, our findings emphasize that a flexible visual memory can effectively incorporate new data, improving performance both in and out of distribution. Section Summary. In this section, we explore the capabilities of a visual memory system that allows for flexible lifelong learning by seamlessly integrating new out-of-distribution classes without retraining, maintaining high accuracy on both in-distribution and new classes. We also demonstrate that increasing the size of visual memory enhances model performance, even with billion-scale unlabeled datasets, while showing that this scaling benefits out-of-distribution performance, crucial for continual learning. Section: Flexible removal of data, machine unlearning. In this section, we discuss the flexible removal of data through a process known as machine unlearning. The world is dynamic, and beyond adding new data, we often need to eliminate the impact of specific training data from a model after it has been trained. Various complex methods are being developed to achieve this, which can be quite challenging when a model has millions or billions of weights. However, for models with a clear visual memory, unlearning becomes straightforward. It's as simple as deleting a sample from that memory. For example, after incorporating the NINCO dataset into our visual memory, we can efficiently remove any NINCO sample while maintaining excellent performance on key metrics. The algorithm is lightning fast. It does not harm the model's performance on retained data or other tasks, and it completely unlearns the specified data. We wonder if machine unlearning can be effectively managed with visual memory. If the embedding model is trained on data that needs to be unlearned, it remains a challenge. However, if it is trained on a safe, general dataset and we later add data for potential unlearning into the visual memory, then unlearning becomes as easy as deleting a data point. This approach is particularly useful for tasks involving private data, as we can train on public datasets to learn general features while keeping private data in local visual memory to protect privacy. Next, we explore flexible data selection through memory pruning. The ability to remove certain data points is not only useful for unlearning but also beneficial for dataset pruning, which focuses on retaining only valuable samples. The challenge lies in determining whether a sample is helpful or harmful in standard models. The ideal method would involve training numerous models, but current approaches aim to approximate this costly process. In contrast, in a visual memory system, we can easily see which samples influenced a decision. For any given query image, we can identify the neighboring samples that contributed to the decision and assess whether they were beneficial or detrimental. We propose visual memory pruning, where we evaluate sample quality by comparing the ImageNet training set against a visual memory of the same dataset. This requires minimal computation and allows us to track how often a neighbor contributed to incorrect decisions, giving us a quality estimate. We can then exclude low-quality neighbors either by completely removing them or by reducing their influence. Our results show that both pruning methods enhance ImageNet validation accuracy, with soft pruning yielding greater improvements than hard pruning. Given the speed of observing outcomes in visual memory models, we are optimistic that our pruning strategies can be further refined. Lastly, we discuss the ability to flexibly increase dataset granularity. Unlike static classification, a visual memory model can adapt its understanding as new information becomes available. We tested this using Dino v2 VIT-L14 embeddings on the iNaturalist 21 dataset, which contains a large variety of animal and plant images. We simulated the discovery of a new species by gradually adding exemplars for new species into memory. Our findings reveal that even before adding any examples of a new species, we can accurately place it in the taxonomic tree. Adding just a few images significantly boosts accuracy, even in scenarios where training a classifier would typically struggle due to limited data. Moreover, increasing samples for the new species not only enhances its accuracy but also positively impacts the entire taxonomic hierarchy. This suggests that visual memory is well suited for hierarchical classification tasks, especially in situations where data for new concepts is initially scarce but later becomes more available, such as in fraud detection, personalized recommendations, and scientific research. Section Summary. In this section, we discuss the concept of machine unlearning, highlighting how models with visual memory can efficiently remove specific data influences, making unlearning as simple as deleting a data point. We also introduce visual memory pruning, which allows us to assess and improve data sample quality for better decision-making, and demonstrate how our approach can flexibly enhance model accuracy as new data becomes available, particularly in hierarchical classification tasks. Section: Interpretable and Attributable Decision-Making. In this section, we express our gratitude to Kevin Swirsky, David Fleet, Bin Kim, Hagen Soltau, Majid Hadian, Kaifeng Chen, Mojtaba Said Hosseini, and Sung Jin Wang for their valuable feedback and discussions. We also thank Mike Moser for his helpful comments on our article draft.